Okay, good morning. Can you hear me and see my screen?
Yes, ma'am.
Yes, ma'am.
Okay. So we were doing various kinds of tests in the last class. This is going to be my last class. So I'm going to start with Fisher's t-test, which, as you know, is a two-sample test of means. So the statistic which you have on the last line, this is the t-statistic, and we know that if the null hypothesis is true, then this follows a t-distribution with n1 plus n2 minus 2 degrees of freedom. We have to make a strong assumption here. The assumption is that the two populations have the same variance. If that is so, then we can estimate this common variance using what we call the pooled variance using the formula which is given on this slide. So depending upon the alternative, if according to the alternative, x has a larger mean than y, we would reject on the right tail, and conversely, if the alternative says that x is a smaller mean than y, we will reject on the left tail. By symmetry, note that one critical value will be the negative of the other. So these critical values will be given for you. If you have a two-sided alternative which just says that x and y don't have the same mean, then we reject in both the tails. But in this case, to keep the overall level of significance at alpha, we have to use a probability of alpha by 2 in each of these tails, so that the total probability remains alpha by 2 plus alpha by 2 equal to alpha. So here is an example where we want to check whether two steel producing factories have the same output performance or not. Our random variables x and y are the daily outputs. So these obviously vary from day to day, so they're random. We assume two normal distributions, and we assume that these populations have the same variance. So in that case, we estimate the pooled variance. We construct the observed t-statistic using the sample means and variances and find that it's equal to 2.11. For any problem, you will be given the critical value. So here you are given that the critical value is 2.042. As 2.11 is greater than 2.042, you reject the hypothesis mu A equal to mu B and conclude that mu A is greater than mu B. Now contrast this with another kind of two-sample problem, except that your data now comes in pairs. So here are some examples. The first example is the height of brother and sister. In the previous two-sample problem, we assumed x and y were completely unrelated. Now you can assume that there might be genetic factors which make the heights of brothers and sisters similar. So in this case, people expect x and y to be correlated. This kind of a testing situation is called a paired testing situation. Similarly, marks of a student in physics and mathematics. Again, you can think of this as correlated data. So here we want to compare the height of brother and sister. We want to test for the equality of means. Similarly, we want to test for equality of means in physics and mathematics. But the difference here from the previous Fisher's t-test is that the data are paired. For paired data, the common distribution is what we call a bivariate normal distribution. It's an extension of the simple normal distribution, which you have been looking at. So this has 5 parameters: the two means, the two variances, and the correlation. So that is what this notation means. XY jointly means XY follows a bivariate distribution, where the parameters are mu x, the mean of x, mu y, the mean of y, sigma x squared, the variance of x, sigma y squared, the variance of y, and rho xy is typically used to denote the correlation between x and y. So here we want to test mu x minus mu y. The difference is that I'm going to define a new random variable. So I'm going to define z as the difference between x and y. So note for the previous example, testing that the mean height of brothers is equal to the mean height of sisters is the same thing as saying as the mean height of the difference in heights between each brother-sister pair is 0. So that is what I'm going to do. I'm going to calculate the differences z equal to x minus y. Once I have the differences, I'm going to ignore the original data x and y, and I'm going to base my test on z. So based on z, my problem is now to test whether the mean of z is 0. In general, the mean of z is mu x minus mu y. The variance of z, I can calculate the variance of z using some formula, but note that it depends on sigma x square, sigma y square rho, and all of these are unknown. So I now have, in terms of this new variable z, I now have a situation where I want to test for the normality, for the mean being 0, but I don't know the variance. Now, if x and y are normal, it can be shown that z also has a normal distribution. So this, in terms of z, it is now a one sample problem of testing whether the mean is 0. So I can construct the t-test for testing this. So my statistic is root n. The mean is z bar. So I'm now behaving as if my data is z. So z bar minus theta, where theta is whatever is said under h naught, usually theta is 0, divided by the standard error of z. So given x and y, I can calculate z and I can find the sample standard deviation. So this will follow a t distribution with n minus 1 degrees of freedom. And I can construct my critical region for this statistic depending upon whether my alternative is theta positive, which is the same thing as saying mu x greater than mu y, theta negative, which means mu x less than mu y, or theta not equal to 0, which is mu x minus mu y. So if you have paired data, what you need to do is to calculate the differences. Once you do that, the problem reduces to the one sample problem with unknown variance, which you know how to solve. Now here is another problem where we want to check whether if the mean earnings of husbands and wives are the same. So you can assume that there is some correlation between the earning of a husband and a wife due to socioeconomic factors. So let me assume that my random variables are the husband and wife's monthly incomes. My data is of 25 households. For each of these households, I have information on the husband's income and the wife's monthly income. And I'm not given the raw data. I'm given that X bar is 30,000, Y bar is 25,000. I'm also given Sx square, Sy square, and Rxy, which is the sample variances and correlation coefficients. So note that what I'm interested in is Z equal to X minus Y. Now I know that Z bar will be X bar minus Y bar. This turns out to be 5,000 for my sample. I also have a formula for calculating Sz square in terms of Sx square and Sy square. So this, if you do the calculations, can be obtained. And after substituting this in the test statistic, I find that it's equal to 96.52, which is a huge value. I said I have data on 25 households, which means n minus 1 is 24. So if you look at the t critical region value of t with n minus 1, which means 24 degrees of freedom, it's 1.71. My observed t statistic is huge, much greater than this value of 1.71. So we reject H naught and we conclude that husband's incomes are significantly greater than wife's incomes. The previous tests we have done are all in terms of what we call the critical value. So we calculate our test statistic and we calculate a critical value based on the level of significance, and we compare the two, and depending upon the alternative we take our decision. Now there is another way to do the test which depends not on the critical value but on something called the p-value. So let's see an example. Suppose we have a single sample problem and suppose that the data is normal and we want to test something like this: mu equal to mu naught against mu greater than mu naught. So the critical region, for the critical value approach, you know that we need to calculate x bar and compare it to the critical value c, where c is given by mu naught plus sigma by root n tau alpha. Let me assume that sigma is known. So in that case, this is the z test which you can perform. Now the way you perform the test is you get your data, you calculate the observed value of x bar. Here it's denoted by small x bar with a subscript of obs to denote observed. You compare it to C, and if it's greater than C, you reject H naught because under the alternative mu is greater than mu naught. For the p-value approach, we proceed a little differently. For the p-value approach, you first calculate x bar observed, and then we find this standardized value of tau observed. So tau naught is notation for the standard normal distribution. So tau observed is root n x bar observed minus mu naught divided by sigma. The p-value is then defined as the probability of getting the observed or a more extreme value, where by more extreme I mean that more likely to support the alternative. Now under the alternative we expect x bar to be larger than mu naught, which is the same thing as saying that I expect a large positive value of tau observed. So I will say that the test statistic is more extreme if it is greater than tau observed. So again, to repeat, the p-value is the probability of observing whatever value you have observed or a more extreme value, where extreme means it is more supporting the alternative. So if I have a right tail test, my p-value is defined as the probability of tau being greater than tau observed. So I look at the right tail. Now, if tau, since the probability of tau greater than tau alpha, the critical value is equal to alpha, that is how tau alpha is defined. If p will be less than alpha if tau observed is greater than tau. So the area to the right is less if tau observed is greater than tau. Tau observed, this means, is further out in the right tail. P will be greater than equal to alpha if tau observed is less than equal to tau alpha. So it is more towards mu naught than it is towards the tail. So a small value of P indicates that the alternative is likely to be true. So again, understand this. If the p-value is small, it indicates that tau observed is larger than tau alpha. So the smaller the p-value, the more likely it is that the alternative is true. So using the p-value approach, we will reject if the p-value is very small. And by very small, I mean that the p-value is less than the level of significance. So for the critical value approach, we calculate our test statistic, we compare it to the critical value, and depending on the alternative, we take our decision. For the p-value approach, we calculate the p-value, where we define the p-value as the probability of getting a test statistic which is at least as extreme as my observed statistic. The word extreme means more likely to support the alternative. The way I use the p-value is I compare it to the level of significance, and if it is less than the level of significance, then I will reject the null hypothesis. So tau alpha is obtained from this red line. It is that value for which the area to the right is alpha. If I get an observed value of tau, which is more extreme, which means it's more likely to support the alternative, it will be more out in the tails, and you can see that the area will be smaller. So that is why we reject the null if the p-value is smaller than alpha. So here is an example using the p-value. Suppose we are given sigma square equal to 256. We've looked at this example before. We want to test that the null that the mu is 200 against the alternative it's greater than 200. And we have a sample of size n. So my critical region, if I do that calculation, mu naught plus sigma by root n times tau alpha, it turns out to be that the critical value is 202.624. So my observed x bar from this sample of size 100 turns out to be 204. My tau observed is, using this value, it turns out to be 2.5. And the p-value, which is the probability of tau being greater than tau observed. So in this case, the probability of tau being greater than 2.5, it can be calculated as being equal to 0.0062. So how do we use, this is the p-value of this test. How do we use the p-value? We compare it to the level of significance. So we compare it to 0.05. And because it is less than 0.05, we will reject H naught. Now suppose instead of 204, my observed x bar turned out to be 201. So I do the same calculation. I calculate tau observed, which in this case is 0.625. I next have to calculate the probability of tau being greater than 0.625, which in this case is 0.266. My next step is to compare it with the level of significance. And here, because it is larger than the level of significance, I am not able to reject H naught. So to use the p-value, you have to calculate the p-value using some tables or software. Compare it to the level of significance. If it is smaller than the level of significance, then you will reject the null hypothesis. Suppose we had an alternative which said mu less than mu naught. So you know how to use the critical region in this case. You have to calculate x bar. You have to compare the cutoff, the critical value, which is now mu naught minus sigma by root n tau alpha. Or you can equivalently say that the critical region in terms of tau is that root n x bar minus mu naught by sigma is less than minus tau alpha. So you have to take the mu naught to the left side and multiply by root n by sigma. Then you can see that the two statements are equivalent. Now, if we want to use the p-value approach, then we calculate x bar observed. We calculate tau observed as for the mu greater than mu naught case. The p-value is now defined as the probability of tau being less than tau observed. So tau observed is that value which you know, because the alternative is of the type mu less than mu naught, it must now lie in the left tail. So here is tau alpha, the red line, the red vertical line corresponds to tau alpha. You can see it must be negative. And the area to the left is now 0.05. 5, which means that the area to the right is 0.95. So the way we use it is the same. We compare P to the level of significance, and if it is small, we reject. So as an example, suppose we want to test H naught mu equal to 200 against the alternative mu less than 200. You can do the calculation mu naught minus sigma by root n times tau alpha. The critical value turns out to be 197.376. So using the critical value, you would reject if x bar is less than 197.376. Instead, if you want to use the p-value approach, you calculate x bar observed, turns out to be 197 for my sample. You calculate tau observed, which is given by root over 100, n is 100, times 197 x bar obs minus 200, which is mu naught, divided by sigma, which is 16. And this turns out to be equal to minus 1.875. The next step is to calculate the p-value, which is given by probability tau less than tau observed. So my tau observed is minus 1.875. I do this calculation and it turns out to be 0.0304. So this I now have to compare as before to alpha, which is 0.05. And since it is smaller than 0.05, my decision is that I can reject H naught. If I have a two-sided alternative, then as before, I calculate tau observed, and my p-value is now, okay, so I calculate tau observed. So note that tau observed can be positive or negative. If you look in the expression for the p-value, you see that there is modulus of tau observed. So what that means is it's just the value of tau observed without the sign. So if your value of tau observed, it turns out to be, suppose as for this example, the value of tau observed turns out to be minus 1.875, then modulus tau observed will be just 1.875. We ignored the sign. So you ignore the sign and the p-value will now have two terms, the probability of tau being less than minus mod tau ops plus the probability of tau being greater than mod of tau ops. Where mod of tau ops, it denotes the absolute value of tau without the, of your observed tau without the sign. The decision rule is the same as before. You compare the p-value to the critical value. If it is smaller than the critical value, then you reject the null. We have been looking at testing for the normal distribution. Let us look at test for another common distribution, which is the binomial, or in case of the binomial size being 1, this is also called the Bernoulli distribution. So let's suppose that x1 to xn are n Bernoulli trials. You can think of tossing coins, for example. So it's Bernoulli if the trials are independent and each has two outcomes, success and failure. So for tossing the coin, it would be two outcomes, head or tails. So let's suppose that head is a success and the probability of this is pi. So each xi is measured as either 0 or 1. 1 denotes a success. And I want to test h naught pi equal to pi naught against the alternative that pi is greater than pi naught. So here's a concrete example. We want to test if the probability of head in tossing a particular coin is 0.6 or greater than 0.6. My data is based on 20 tosses of the coin, and I observe S, which is the total number of heads in 20 coins. Now, from previous notes, you should know that S follows a binomial distribution with n equal to 20 and success probability equal to pi. So since under the alternative pi is greater than pi naught, in this case pi naught is 0.6, under the alternative we will expect S to be large. So we should be able to get some C. If we use the critical value approach, we should be able to get some C where C satisfies that the area to the right is alpha. Now, because S is not continuous, it is not always exactly possible to find this C. So rather than go into the complications, this is what you would do for the p-value approach. So we calculate S obs, which is your observed sample. Your p-value is the probability of getting an S statistic which is at least as extreme as S obs. So because my alternative is of the right tail type, my alternative says that pi is greater than pi naught, the p-value for this case will be given by the probability of S being greater than equal to S obs. And because S obs has a binomial distribution, we can easily calculate this by summing the terms of the probability mass function. So this is how you calculate the p-value. The use is the same as before. We compare the p-value to the level of significance, and if it is less than the level of significance, we will reject the null hypothesis. Now to test H naught against the alternative pi is less than pi naught, here my test will be based on the left tail. So the p-value is given by the probability of S less than equal to S obs. So again, using the binomial probability mass function, I can add the terms from 0 to S obs and calculate the p-value. My decision rule is the same as before. I compare the p-value to the level of significance, and I will reject if the p-value is less than the level of significance. So similarly, I can have the p-value for a two-sided test. So for the two-sided test, for a two-sided alternative, pi not equal to pi naught, I would calculate two probabilities. I would calculate the probability of S being greater than equal to S obs, as well as the probability of S being less than equal to S obs. If either probability is less than alpha by 2, I will reject H naught at the alpha percent level. So alpha, let's suppose, is 0.05. So I would compare each of this to the 0.025 value, and I will reject H naught if either of these probabilities is less than 0.025. It's not quite like the normal distribution because the distribution is not necessarily symmetric like the normal distribution. There is another way to test for the binomial proportion, which you can use if the sample size is large. So S by n naught, S is the total number of successes in a total of n trials. So P equal to S by n is the sample proportion of successes. It's possible to find the mean value, expected value of P, and show that it's equal to pi, and the variance of P, you can calculate it using your expression for the variance of S for the binomial distribution, and it turns out to be pi into 1 minus pi divided by n. So if n is large, then according to a result which we call the central limit theorem, it's possible to show that this quantity, p minus pi divided by root over pi 1 minus pi by n, it follows a standard normal distribution for large n. So to test H naught pi equal to some pi naught against the right-sided alternative, we can use this sampling distribution of this test statistic, p minus pi naught divided by root over pi naught y minus pi naught by n. And according to the central limit theorem, this will follow the sampling distribution of this quantity. It will be the standard normal under the null hypothesis. So because under the alternative, my pi is greater than pi naught, I will derive the critical value as I would derive the critical value for a right-tailed normal test, which means that I will reject H naught if tau observed is greater than my tau alpha. So for the previous example, if instead we want to use the large sample approach, note that my S observed was 15, which means that my pi was 15 over 20 minus pi naught, which is 0.6, divided by root over pi naught, 0.6 times 1 minus pi naught, which is 0.4, by 20. So my tau observed, it comes out to be 1.37. I can compare it to the critical value, which is 1.64. And since it is less than tau naught, I don't reject H naught. Similarly, if I want to test pi less than pi naught, I can proceed exactly as I would for the normal mean, for testing the normal mean. So this is as if you are testing a normal mean, and use the critical value of minus tau alpha. And similarly, I can extend this large sample test to the case where I'm testing for binomial proportion pi being some specified pi naught against a two-sided alternative that it is not equal to pi naught. Now, just like for the normal distribution, we can have a two-sample problem. We can also have a two-sample situation for two binomial distributions. So here is an example where we have an election between two candidates, between several candidates, and we're interested in two of the candidates, and we want to know if they have an equal chance of winning or if the first candidate is more likely to win. So note that this is like a binary situation where each vote can be cast for one of these two candidates. So we are only considering the votes which are cast for one of these two candidates. So S1, let this be the total number of votes cast for the first candidate. S2, the total number of votes cast for the second candidate. P1 and P2 are the corresponding proportions. We are interested in testing if the underlying population probabilities pi 1 and pi 2 are the same, or if the first candidate has a larger probability pi 1, which is larger than pi 2. So here too, if the sample sizes N1 and N2 are large, we can use the central limit theorem and reduce the problem to a normal testing problem. So in this case, here is the statistic which follows the standard normal distribution. It's given by P1 minus P2. So the difference of the sample proportions in the numerator. In the denominator, we have something called P bar into 1 minus P hat times 1 minus P hat, and then 1 over N1 plus 1 over N2. N1 and N2 are the two sample sizes. P hat into 1 minus P hat. If you recall, the binomial variance is given by, for the first population, pi 1 times 1 minus pi 1 by N1. For the second population, pi 2 times 1 minus pi 2 by N2. But under the null distribution, we have pi 1 equal to pi 2. So it's as if the two populations, we don't have a two sample situation, but we have a one sample situation, and we can get a better estimate of this common value of pi if we pool the data. So that's exactly what P hat is. It is the estimate of the common probability of success if the null distribution was true. So in the numerator, it's the sum of the total number of successes, and in the denominator, it is the total number of trials, S1 plus S2 divided by N1 plus N2. The critical regions are obtained as you would for the normal test. So if you're testing pi 1 greater than pi 2, my critical region is test statistic greater than tau alpha. If you're testing pi 1 less than pi 2, it's test statistic less than minus tau alpha. And if I'm simply testing pi 1 not equal to pi 2, then it's test statistic less than minus tau alpha by 2 or greater than tau alpha by 2. Now we've been looking at the case of two populations. It is not necessary that we always want to compare two populations. We can easily think of a situation where we might want to compare, say, 5 populations. So in the previous example, let me look at me. So we were looking at income in one of the examples. So suppose I want to compare the average income, but I don't want to compare it for two populations. So say I want to compare the average income across all the states of India. So in that case, it's not two populations, it's 28 populations. So how can you compare means for more than two populations? So we're going to refer to these populations as groups. So let's assume that I have P groups. These groups are G1, G2, GP. For my example, they would be the 28 states. P would be 28. And I would have 28 groups comparing to the 28 states. So I'm assuming that I have one sample from each of each state. I'm going to assume that within each state, the income, it follows a normal distribution. Let me assume that for the jth state, this mean is given by mu j. And I will assume that the variance is sigma j square. Now you have seen that when you do a two-sample t-test, we have to make the strong assumption that both the samples have the same population variance. So similarly here, I have to make the equivalent assumption. I have to assume that all the P populations have the same variance. So let me assume that sigma 1 square is equal to sigma 2 square is equal to sigma 3 square is equal to sigma P square, and that this common value is given by sigma square. The null hypothesis I want to test says that all the 28 states have the same mean population. So I want to test mu1 equal to mu2 equal to, in my case, mu28, in general equal to mu p. And the alternative says that at least one pair must be unequal. So at least one state has an income, which is average income, which is different. So here is my sample from the jth population. Let me assume that it's of size nj. My total sample size, which means the pooled sample size across all the states, is obtained as n1 plus n2 up to np. The test I'm going to do, the name is written on the slide. It's called a one-way analysis of variance. So to do this one-way analysis of variance, what I'm going to need is each of the group means. So for my example, it means that I need the average sample income for each of the states. I denote this for the jth state by xj bar. I also need what I call the grand mean, which is the mean of the total pooled data. So if I'm given the group means x1 bar, x2 bar up to xp bar, I can calculate this grand mean, which is now denoted by x double bar, as 1 over n. N note is the pooled sample size. 1 over n, sum of these quantities, not just the sum of the xj bar, because the sample sizes for each states are different. So n1 x1 bar plus n2 x2 bar up to np xp bar, that is the numerator, and in the denominator it is n1 plus n2 plus np. So if you do this, you will get the grand mean, which is as if we have pooled the entire data from all the groups. The next quantity I need is something called a sum of squares. The analysis of variance technique depends on this sum of squares. So the total sum of squares, the formula is here. It is the sum of the deviation of every value in the pooled sample from the grand mean. So I pool the entire data from all 28 states treated as one sample, and I find the sum of squared deviations from the mean. This I refer to as the total sum of squares, and you can see that there is another quantity mentioned alongside. It's the degrees of freedom. This total sum of squares has a degrees of freedom which is equal to the sample size minus 1. The next quantity I need to calculate is what I call the between sum of squares. So this is the sum of p terms, 28 terms for my example. It's like a weighted sum of squared differences. The deviations are xj bar. So this is the mean for the jth state minus x double bar. So I find the difference of each of the state means from the grand mean, and I square this difference. I multiply it by a weight in j, which is the sample size for the jth state, and then I sum all the quantities. This I call the between group sum of squares. And then I also have the within group sum of squares, which is given by considering each state, finding the squared deviation of the state mean from the grand mean, of the state observations from the state mean. So say I take West Bengal and I have a sample of size 100 from West Bengal. For each of the 100 observations, I need to find the deviation from the mean for West Bengal, square them, and add them. So similarly, I do this for all the states, and then I add it across all the states. This quantity is called the within group sum of squares. So that sounds tedious, but actually we don't really need to calculate the within group sum of squares, because we have this relationship that the total sum of squares will always be equal to the sum of squares due to the groups plus the within sum of squares. It's not necessary for you to understand the derivation, so just understand that this kind of a decomposition of the sum of squares will hold. The total sum of squares will be equal to the sum of squares due to group plus the within sum of squares. Now suppose H naught is true. If H naught is true, what was H naught again? H naught said that all the groups have the same mean. So if H naught is true, we will it follows that SSG must be small. So why is that? Because SSG is the difference of each state mean from the pooled mean. So if all the states really have the same mean, we will expect that each of the group means will be similar to the pooled mean. And because of this, the difference xj bar minus x double bar will be very small. So if H naught is true, we will expect that SSG will be small. And because we have the decomposition that SST equal to SSG plus SSW, it conversely means that SSW must be large. Similarly, if H naught is not true, it means that SSG must be large. So in this case, the means are different. And because of the decomposition we have, it conversely means that SSW must be small. My S statistic is then defined by the ratio SSG by SSW. So not quite by the ratio. We also have to divide each sum of squares by the quantity which I mentioned was the degrees of freedom. This is so because I need to get a known sampling distribution so that I can calculate the critical value or the p-values. So note that under the alternative, my SSG will be large. And because of this, I will reject the null hypothesis if my SSG is large and SSW is small, which is the same thing as saying that my F is large. So that's what this says. F distribution, it's possible, it has two parameters, 2 degrees of freedom, something called a numerator degree of freedom and a denominator degree of freedom. So you have to look up the right tail critical value for the specified degrees of freedom. And if your observed F is larger than the sample, than this critical value, we reject H naught and conclude that the group means are not the same. And the next and probably the last topic is interval estimation. So we've looked at estimate. The idea of estimate is that we have some random variable x, which has some probability distribution. If it is continuous, then it has a probability density function. If it is discrete, it has a probability mass function. In each case, I denote it by small f. Small x are the observed values of the random variable. So for Bernoulli data, for example, it was 0 and 1. For continuous data, it can be any real value. And there is some parameter which defines this probability distribution. So for the normal distribution, it can be the mean or the variance or both the mean and variance. For the Bernoulli distribution, it can be the success probability. So we have some unknown parameter theta, and we want to estimate this unknown parameter from the data. When we were doing estimation, we looked at several alternative ways to find a good estimate. I mentioned least squares. I mentioned minimum variance unbiased estimators. I mentioned the maximum likelihood estimator. In each case, we get an estimate of theta with some good properties. But the point is that we get one single estimate of theta. So if I have binomial data, say, and I'm trying to estimate my success probability, and I observe that out of 10 heads, out of 10 tosses of a coin, I have 5 heads. It means that my sample estimator has a value of 5 by 10, which is half. So my estimate for the unknown probability of getting a heads is half. The point here is that my estimator is one single value. The idea of interval estimation is that I don't report one single value as my estimate. Instead, I report a range of values. So for my Bernoulli example, I won't report something like theta hat equal to half. I want to report a range of values that theta hat probably lies between this lower bound and this upper bound. The lower bound and upper bound are calculated based on the sample. So that is what this notation says here. Given the sample x, which is x1, x2, xn, given a sample of size n, I calculate two bounds. One is t1x, which is the lower bound. Another is t2x, which is the upper bound. And these bounds are calculated such that the probability of theta, the true unknown parameter theta lying between the two bounds, is some quantity 1 minus alpha. So alpha is very small, maybe 0.05, in which case 1 minus alpha is large, 0.95. So suppose alpha is 0.05, then this statement says that I am 95% confident that theta lies between T1x and T2x. This interval, T1x, T2x, it's called a confidence interval for theta. And this quantity, 1 minus alpha, is called the confidence coefficient. So suppose we want to find a confidence interval for the normal mean, and we have a sample of size n from this distribution. So to make it simpler, let me assume that sigma square is known. We know that for any value of mu and any value of sigma, this quantity root n x bar minus mu over sigma follows a standard normal distribution. So I know this from properties of sampling distribution of the normal mean. So if this is so, then the probability of this quantity lying between the two cutoffs, a lower cutoff of minus tau alpha by 2 and an upper cutoff of tau alpha by 2, this probability must be equal to 1 minus alpha. Now I can manipulate these inequalities so that mu remains in the middle. Then I get the equivalent statement that the probability of mu lying between these two cutoffs, the lower cutoff is now x bar minus sigma by root n times tau alpha by 2. The upper cutoff is x bar plus sigma by root n tau alpha by 2. The probability of mu lying between these two random cutoffs is 1 minus alpha. So if you compare with the previous slide, it means that we say 100 times 1 minus alpha % confidence interval. So basically, if alpha is 0.05, 1 minus alpha will be 0.95. 100 times that will be 95. So the 95% confidence interval for mu is x bar minus sigma by root n. My alpha is 0.05, so tau 0.025 and x bar plus sigma by root n times tau 0.025. So basically x bar plus minus sigma by root n times tau 0.025. These are the two confidence bounds, and we are 95% confidence that mu lies between these two bounds. Now, if sigma square is unknown, then we can't obviously calculate these confidence intervals because they involve sigma. However, we know that if sigma square is unknown, then this quantity, root n x bar minus mu, so because we don't know sigma, we replace it by s. And if we replace it by s, the distribution normal, the standard normal, gets replaced by the t distribution with n minus 1 degrees of freedom. So we have this kind of an equivalent distribution statement for the t distribution. So note that the t distribution is also symmetric like the normal distribution. So this quantity, root n x bar minus mu by s, it must lie between the lower alpha by 2 and the upper alpha by 2 points of the t distribution with n minus 1 degrees of freedom with probability 1 minus alpha. Again, I can manipulate these inequalities so that mu comes in the middle. And in that case, the probability of mu being greater than x bar minus s by root n, t n minus 1 alpha by 2, and x bar plus s by root n times t n minus 1 alpha by 2, this probability will be equal to 1 minus alpha. So if sigma is unknown, my sigma gets replaced by s, and tau gets replaced by t n minus 1 in the formula for the confidence interval. So here is a problem. Suppose I have a sample of size 25. My x bar is 120. I don't know sigma square. I'm given s square equal to 64. To calculate the confidence interval, I need the critical value for t. So note that if I have a sample of size 25, my t will have n minus 1, which is 24 degrees of freedom. And I also need to have the probability of alpha by 2. So if I assume alpha is 5%, which means that I want a 95% confidence interval, alpha by 2 will be equal to 0.05 by 2, which is 0.025. It's possible to look this up from tables or software, and it turns out that this value is equal to 2.064. So this is how you calculate the confidence interval. X bar, which is 120, minus s, so s square is 64, which means s is 8, by root n is 25, so root n is 5, times the t value which I found, which is 2.064. This is the lower bound, and the upper bound, so there's a typing mistake here, it should be 120 plus 8 by 5 times 2.064. So this comes out to be equal to 116.69 and 123.30. So I'm 95% confident that the true unknown population mean lies between these two bounds with probability, with probability 0.95. To find the confidence interval for pi, we can also use the large sample formula. So here we will use the fact that for any value of pi, this quantity p minus pi, p is the sample proportion of successes. Pi is my unknown probability of a success. I use the fact that if n is large enough, then this quantity p minus pi divided by root over p 1 minus p by n, it follows a standard normal distribution. So if this follows the standard normal distribution for large enough n, it must be that the probability of this quantity lying between the lower alpha by 2th tail and the upper alpha by 2th tail, this probability is 1 minus alpha. So again, I can manipulate the inequality and bring pi in the middle. My two cutoffs turn out to be p minus root over p 1 minus p by n tau alpha by 2 and p plus root over p 1 minus alpha by 1 minus p by n tau alpha by 2. So p is here the sample proportion. So that is what I had for today. And that's all I have for this class. Do you have any questions?